We're wrapping it up a bit with this example here. Same instructions as a couple of examples ago. We're going to sketch a region of solid disk or washer. We're going to take the region that's bounded by y equals x cubed, y equals 1, and x equals 2, and we're going to rotate it about the line y equals negative 3. So of course this is different because we're not rotating it about a coordinate axis. First, a drawing. Here's our region. It's bounded by y equals x cubed, y equals 1, and x equals 2. Now our axis of rotation is y equals negative 3. So let me just draw that, and then I'm going to indicate that's how we're rotating it, which means we want a perpendicular or vertically oriented representative rectangle, right? It should be perpendicular to the axis of rotation. Now this is about to get ridiculously large. The lower portion of the region is defined by y equals 1, and then the axis of rotation is y equals negative 3. There are 4 units between those, which means that the whole of my washer, this is going to be a washer, right? Because there's a gap between the region and the axis of rotation. That gap has a radius of 4. So I'll label that as r equals 4. The outer radius is variable. Here it's about 2 bigger. When I say 2 bigger, I mean like this is about like 2-ish there. So I made this, I don't know, somewhere around 2-ish there. But as far as our solid is concerned, we have a hole on the top. And then I'm supposed to take this part and repeat it over here. So this thing pretty much is the solid that we're dealing with. Now the outer radius for the washer, there's the function height, right? I didn't like that there. Okay, there's the function height. And then the radius is the distance between that value here and the axis of rotation. Well, this distance here is f of x sub I, we'll say. This distance here is 3. We can see that, y equals negative 3, right? So this outer radius, call it r, uppercase R, is equal to x cubed plus 3. I hope you can see that, right? So for any particular x value, this function height is x cubed. And then this is an additional distance of 3. So with all of that, to set up the integral for our volume, we have v equals pi. I'm putting the pi in front of the integral because it really doesn't matter where we put it. The region itself spans, x goes from 1 to 2. And then the outer radius is x squared plus 3. And we're going to square that. The inner radius is 4. And we're going to square that. And then we have the entire thing times dx. Folks, the integrating isn't the hard part of this. It's the setting up. And I had this as x squared here. It's x cubed plus 3, the quantity squared, right? And our answer turns out to be 471 pi over 14. So like I say, the integrating itself isn't like real bad. It's just using the power rule. The tough part here is dealing with the 2 radii, especially because the axis of rotation isn't a coordinate axis. So much easier when it is. So let's generalize this when we have an axis that's not a coordinate axis. When the axis of rotation is not a coordinate axis, we can generalize the volume of a solid by saying that v equals pi times the integral from a to b r squared dx. Now that's not really a different formula. We're saying r is the distance between the function and the axis of rotation. And then in the case that we have a washer, we have uppercase r squared minus lowercase r squared. And lowercase r is the distance between g and the axis of rotation. Now this can go down several ways. Now this second formula with the big R squared minus little r squared, I can say that because it's a bigger radius and a smaller radius. I mean, I'm not stuck to uppercase and lowercase. Gosh, that gets annoying. Anyway, we were looking at that because we had a region that was defined by 2 curves, right? Y equals x cubed and y equals 1. But for what I'm about to do, let's just focus on the first formula here, because if you have an understanding of how to set up R, big R, then you will easily translate that into finding little r. So suppose we have here a region defined by a function f. When we rotate about the x-axis, then f is equal to r, no big deal. Now what if we take that region and we lift it up a bit and rotate it about y equals c? Then our radius is the distance between a function value and the constant. So here we've got that r is equal to f minus c. And that's what's meant by r is the distance between f and the axis of rotation. Now let's introduce a gap between the region and the axis of rotation. Let's say the bottom of the region is now y equals c. The outer radius r is still equal to f. Right, that's the distance between the function and the axis of rotation. The inner radius is going to be c minus 0, right? It's the distance between c and the axis of rotation. So that's not such a big deal. At the risk of making this really complicated, now suppose we have a region that's defined by a function f and a constant c. This c, it could be a function g. It doesn't matter if it's constant. That's not really the point of this. Then we're going to rotate it about the horizontal line y equals d. The outer radius is going to be f minus d, right? The distance between the function and the axis of rotation. And then the inner radius is going to be c minus d, the distance between that edge and the axis of rotation. I hope all of this is making sense. Now we're going to look at our final setup. Same region, defined by f and c, a constant. We're going to rotate, or it doesn't matter if c is a constant. We're going to rotate it about y equals d, but d is now negative. So what now becomes my outer radius? It's still f minus d. What becomes my inner radius? It's still c minus d. Suppose d is like negative 4. Then f minus d becomes f minus negative 4, and that becomes f plus 4, which should make sense. It's the function height plus an additional 4 units, right? And then c minus d would become c minus negative 4, which would then be c plus 4, which again should make sense. If c is 3, let's say, then 3 plus 4 is 7, and that should be the radius, right? So some people think that there are different setups all over the place, and there really aren't. It's always an edge, like a function value, minus the number that represents the axis of rotation. But in the case of rotating it about the x-axis, that's y equals 0. So you got f minus 0. Nobody writes down f minus 0. Here it's f minus 0 and c minus 0, right? Then it becomes f minus c when I'm rotating it about the line y equals c, right? And then it becomes f minus d. It's always the distance between the function and the axis of rotation. And that's true whether we're talking about the outer radius or the inner radius.